I have one day, I guess. So we started to talk about the chain rule, and we also discussed other ways to get those derivatives done. So let me try to follow the example that we have here, just to refresh how we use formulas for derivatives. So there was one that we saw a while ago that deals with a derivative of a square root, which is 1 divided by 2 square root of x. That was a little formula that I recommended you to keep in mind, but I guess that one could always be derived using the favorite power rule formula. So if you take a derivative of some kind of power, then this power will be multiplied by x raised to the power of 1 less. So that was the key formula that we actually utilized most of the time. But for the example here, we can use the fact that when you differentiate that x squared plus 3x and plus 2 inside the square root, then we're going to have the derivative of the square root as 1 over 2 times that square root. And whatever is inside of square root, I just need to copy the way it is. So it'll be x squared plus 3x and plus 2. So next step will be to actually multiply by derivative of what's in the inside. And the inside is 2x. When I take derivative of x squared, it's 2x and plus 3. So this will be my result here. And that's exactly what they actually have here for us in the answer for that example. So you can see that derivative of this inside, or so-called argument of that square root, has to be also present. So I'd like to utilize these ideas for doing some problems in section 2.4, because they're very popular in the exercises. So we already noticed that problems that appear in those sections are quite lengthy, and that's why I don't want to do too much emphasis on those. I just rather just do a couple of exercises and move on, because one can be stuck with this for a long time, and that's what I don't really want to get into much. So I'll just select a couple of problems and notice that they are not going to be very short. So, for example, when I look at 35 in the section 2.4, that deals with x plus 2 raised to the power of 3, looks like. And this is also multiplied by another parentheses with 2x minus 1 inside raised to the power of 5. Then this means that I have to utilize our, remember, f times g, the formula for derivative of a product. So I need to know what is f prime, what is g prime, because when we going to take derivative of product, it's going to look like f prime times g plus g prime times f. That's what we observed in the previous section. So in exercise 35, I can't really avoid going with that formula. So I go with that formula. So I have to take function f, which is here, take its derivative, and this is going to be 3 times x plus 2 raised to the power of 1 less, which is squared, times the chain rule says multiplied by derivative of x plus 2, so it's just times 1, which means nothing. For the other piece, for the second factor, which is a fifth power, I'm going to maybe move this a little bit farther away so it doesn't mess. So g prime will have a 5 on the ground, and the power will be 4 here because the 2x minus 1 needs to be raised to the power of 1 less than 5 times. So the next thing will be taking derivative of 2x, which is equal to 2. So this will be our starting point. So at that stage, we're going to multiply 2 by 5 and get 10 with 2x minus 1 to the 4th. And now I need to set up this entire structure. So I need to put all of this in one single sum. And the f prime, which is without 1 times 1 means nothing, will be 3 times x plus 2 in the parentheses squared. That's my first piece. Multiplied by g itself, and g itself, that's the second piece, right? That's 2x minus 1 in the parentheses to the power of 5. Then we need to plus, right? Because then it's a plus sign here. And then I go with a g prime, the one that I just found here. This is 10 multiplied by parentheses, and the parentheses has 2x minus 1 to the power of 4. And then finally, we get this function f, the first parentheses were square of x plus, actually cube of x plus 2. So this is very tedious, and you can, of course, keep factoring it, but that's not really gonna bring you anywhere. And that's the reason why I would say stop at that stage, and that'd be good enough. I also want to do one more exercise with a quotient to stress analogous formula for the quotients, and that I think, well, doesn't hurt to look at every once in a while, but again, I think it's just a little bit too much. So this section definitely has tedious exercises, but if you do the same couple of problems that I just did, that'd be good enough. So I'm going to do the second one. Denominator has to be squared. So this will be f prime multiplied by g, and then minus g prime multiplied by f. So analogous to the formula that we just utilized for derivative of a product is a derivative of a quotient formula. So when I'm looking at exercise 37 here, then quotient will be inside of my square root. So we're dealing with a square root extracted from, and here comes that 3x plus 1, and denominator is 2x minus 1. So what I'm going to do is treat 3x plus 1 as function f, because we have a division here inside the square root, and 2x minus 1 as a function g. So then I can find that from here, derivative of f will be number 3, and from the second derivative of g prime will be 2. And then, well, then the chain rule will be in play. So then I'm going to have to take that fraction 1 over 2 times square root, put a square root on the outside, and just copy whatever we have inside the square root, 3x plus 1 over 2x minus 1, just like that. And then we're going to have to multiply this by derivative of a quotient, which is up there. And that's my quotient in here. So here's f, here's g. So I'm going to have a g squared, which is 2x minus 1 squared on the bottom. See, I have to have plenty of room to write this down. And then I need to have on the top f prime times g. F prime is 3, right? So I have to multiply it by g. And what is g? 2x minus 1 in parentheses minus. And then I'm going to have the g prime, which is 2, right? And this 2 is multiplied by f, which is my numerator, which is 3x plus 1. So this way, I have myself the answer. Notice this is really unpleasant looking expression. And that's why I just don't want to continue into these problems, because it's all going to be analogous type of a mess. As long as we know we take function on the outside and multiply it by what's inside, that's, I guess, plenty for this part of the story. And they actually continue this farther with various other functions. So I guess this would be something that we utilize in a little bit better shape when we actually start our applications, because at this stage we get very deeply into theoretical math procedures that I just want to abandon and move on to the place that we actually need for this class. Move on to the chapter 3, where we actually going to utilize derivatives to graph functions. And that's the key idea that I wanted to get across today. Why do we really need all of that story of derivatives? So I'm gonna enter chapter 3, and that's what's called graphing various functions. So I'm gonna maybe clean all of this mess real quick like that. Share this screen again. And now we're gonna look at the picture here of the function. And turns out that the graph of it will consist of a couple of main points. So if you were able to plot those 2 points, I marked with a blue, and that point is kind of lower one, and the other one is a higher one, so we call it as a maximum, and the lower we call as a minimum. Then turns out we can connect with a graph that goes down up to this minimum point, and then starts rising up to maximum, and then falls down again as a after the maximum point, the function will be pretty well determined by these two special minimum and maximum points. And it turns out the key idea in finding those points will be to get their tangent lines and to notice that the lines that touch function at those points are both horizontal. Horizontal lines have slopes equal to 0. And that's the key part of this story. So it turns out that I need to find points that have special so-called tangent lines, lines that touch my graph with the slopes equal to 0. And 0 slope, slope means derivative. And that's what we're going to do. We're going to find those points where our derivative is going to be equal to 0. For example, if I check out function such as a 2x cubed plus 3x squared, and also minus 12x and minus 7, then for this particular function, I can try to find its derivative, and we already know how to differentiate. I'll just bring 3 down, so multiplied by 2 get 6 with x squared. Then I multiply 3 by 2 for the next one, and I get 6 times x to the power of 1, so it's just x. And finally, 12x derivative will be equal to 12. So this derivative, I need to set equal to 0. In other words, find those special points, those points where we have the lowest and the highest ones, minimum and the maximum. So I need to solve this equation for 0, and notice that I could just divide by 6, right? So numbers get smaller. So I get a x squared plus x and minus 2 is equal to 0. And then if I solve this equation using factoring, and I guess this is pretty straightforward for factoring, I can break my first term, x squared, as a product of x with x, and then the last number 2 as a positive 2 times negative 1, then I'd be able to actually see that we factored this correctly. And some people can check this out, say, what if I multiply 2x here inside and negative 1x on the outside? Would I get my middle term, which is positive x? Looks like 2x minus x is indeed equal to x. So x plus 2 is the first piece that I set equal to 0, or another factor, x minus 1, that also I set equal to 0, and that gives me 2 special points that we were looking for. They are 1 and a negative 2. And that's exactly what they actually found out here when they did the same process of finding derivatives. So they found that 0.1 and a negative 2 are exactly those where my function has this maximum and a minimum values. So what we concerned with so-called first derivative equal to 0. So we set derivatives equal to 0, and that gives us those special points, minimum and maximum, and then using the fact that we have a function which is a cubic, the largest power of this is 3, right? So it's from family of so-called cubic parabolas. So one end of it goes upwards and the other down, allows us to graph this function. So we have connected this with a cubic-like parabola. So that's what this new chapter discusses in very detail. So I'd like to take an exercise from this section and go through this same process again, so we start to get used to it. The point is, get used to procedure of finding those derivatives and make them equal to zeros. And that's really all it is that we have to do to graph various functions. So let me go to the exercises and take a derivative. So the key idea for us now will be taking derivatives and make them equal to zeros. So let me go to the exercises here. So I'm going to do problem number 10. I'm going to take a derivative of this function. Notice they gave us function of letter t. Well, we already know it doesn't matter what your variable is called, if it's x or t, still pretty much the same thing, right? So we're gonna take derivative, so it'll be f prime and t cube. So 3 goes on the ground and t squared stays with us, right? And the next one is going to be t squared. So 2 will be multiplied by 3, give me 6, and a t with it. So I found derivative. All right, found derivative, set it equal to 0, and solve this equation. How we solve it? We factor it. Take out 3t, that's a common factor, right? So t in the parentheses and plus 2. So it looks like when I solve these equations, because there'd be 2 of those, first is going to be set equal to 0, as well as the second one set equal to 0. So from first, I get t equal to 0. And from the second, I get t equals to -2. So this way, I got 2 special points that should enable me to actually graph this function. And if I want to graph, what I do is I need to get their y coordinates. So if t is found, what is f of t, which is same as y? Well, let me plug in that 0 for the first one. So I find f of 0 and I plug into my function up there. So we get a 0 to the third plus 3 times 0 to the second and plus 1, which is equal to number 1, right? So that's my first point. T is 0, y is 1. Analogously, I'm going to go for the second point when t is equal to -2. Let me get another color. So I plug this in here. So f of, instead of t, I put -2. And again, I just need to utilize my function that now I'm trying to graph. So it'll be a negative 2 to the power of 3 plus 3 multiplied by negative 2 squared. And finally, plus 1. So we got a minus 8 for the first one, right? Then 2 squared is 4 times 3, 12, and added 1. So this will end up being 12 minus 8 is 4 plus 1, 5. Okay, so we've got another point here, and its coordinates will be a negative 2 for t, the first coordinate, and plus 5, the second coordinate. So I'm gonna try to graph now the function that is analogous to what we have above what we have for the cubic parabola, because our biggest power is here, it's t to the power of 3. So first point is 0 for x and 1 for y. That's my point with coordinates 0 and 1, somewhere on y-axis. And the second point with coordinates negative 2 and 5. So I can call the x-axis with a variable t. In fact, in physics, sometimes they like time. So put instead of x, letter t. So here are the 2 points that we found. And now I'm gonna connect them with analogous shape to what we have here. So one end needs to go upwards and the other end needs to go downwards. And this is gonna be a pair like a maximum and a minimum. So with these 2 special key points, we have a very good idea how the graph is going to look like. And the whole, I guess, procedure starts when you take derivative and make it equal to 0. And that's the, I guess, most important part of the story. So what I can do is take another derivative and make it equal to 0, and then I will ask you to do analogous thing. So I can try to do this in the exercise number 11. So I'm going to do 11. Just take derivative and make it equal to 0. That's actually what these problems want us to do here. So if my function f of x here is given as a x cubed minus 3x, and then also subtract 4, then I'll take f prime of x, and this is going to be 3x squared, right? And minus 3x, so just minus 3. So once I found that derivative, I make it equal to 0, and then try to factor. So if you take out 3, then x squared minus 1 will be what you need to factor. And if I factor that out, then I'm going to get 2 parentheses. One is x minus 1, and the other is x plus 1. So I can solve 2 of these little equations, and from the first parentheses, I can see that 1 is going to make it equal to 0. And from the second parentheses, I'm going to see that negative 2 is making it equal to 0. So I've got 2 answers, 1 and a negative 2. So can you also find the derivative of this and make it equal to 0 and tell me what value of x is going to be there? I think it'd be something nice because it's just x squared. They saved it for you, so I'm sure you're gonna like that. So find x for a quiz that makes this derivative equal to 0. So what you do is, well, same thing I just done. First step, find f prime. Second, set it equal to 0, and then you will be able to see what value of x works for this. So that's our little quiz for today. And please don't hurry, take your time. So exercise 11 I done. You don't need to do it for a quiz. Exercise 9. See, I try to put it in red color. 9 is a quiz. So what you need is to find x that makes your derivative equal to 0. And that's all for today. So please take your time, don't hurry.